Hello everyone, welcome to lecture 24 on the online course on Introduction to Microwave and Optical Metamaterials. So today's lecture will be on inhomogeneous and chiral metamaterials. Here's the lecture outline. We'll discuss about inhomogeneous metamaterials, introduce different types of engineered metamaterials in this category, and then focus on chiral metamaterials. Now, what are metamaterials? We have seen that these are basically artificial media which are designed to control light propagation via tailored unit cells, which are also called metaatoms. Now, by controlling the geometry and the material dispersion at the metaatom, novel effects such as negative refraction, optical cloaking, as well as a series of optical analogs to the phenomena known in other physics domain can be observed. Now, inhomogeneous metamaterials are those artificial metamaterials where the arrangement and the properties of their constituent elements will not remain same throughout the material, rather they will vary throughout the material, and that is where they are different from the homogeneous metamaterials where the properties remain consistent throughout. Now, this variation basically enables different regions of distinct refractive indices and permittivities, okay, and that leads to unique and tunable electromagnetic behavior. So, you have different regions having different material properties, right. So, in general, homogeneous isotropic material properties simplify the analysis and the overall design, okay. However, one can try to work on this kind of parameters that allow you some attractive effects, okay. So, you can, like, if you give away this kind of simplification, you will have more control over the electromagnetic properties within the material, right. So, you will see that in last few years metamaterial research has basically focused on those directions, mainly towards an interesting field of cloaking, which is based on transformation optics, okay. And there you basically require inhomogeneous materials or inhomogeneous metamaterials, okay. And these inhomogeneous metamaterials can be treated by varying the metaatom size and geometry with spatial position. So, throughout the metamaterial the things are not going to remain same, okay. So, what are the examples of this kind of thing? So, first example you can think of is magnetic field shielding, okay. It is an important application of lot of practical interest, okay. So, let us look into some example here. So, we will see that shielding by means of inhomogeneous metamaterial will have some added advantage over traditional shielding that we achieve using high permeability material and typically the active magnetic field shielding, which is known as, okay. So, here the relative permittivity values that are used to illustrate the material behavior is considered to be mu r equals 100 in this case. This is the high permeability one, and this is the one with the low permeability, that is 0.01, okay. So, both are the relative permeabilities. Now, what is interesting here is that the magnetic field shielding mechanism basically differs based on the permittivities involved, okay. So, in the first case, which is the high permeability material, you can see that it basically trap or guide the magnetic field within the shield, okay. So, this is the shield, okay, and this basically traps the field within. And in the case of low permeability material, this basically does not allow any magnetic field to enter, okay, and that basically repels the magnetic field. So, that is also another kind of shielding, right. So, you can actually have magnetic field shielding by materials, okay, with different permeability working on different principles. Now, for homogeneous and inhomogeneous materials, okay, you can understand that you can, for the case of inhomogeneous, we are now considering unit cells which are capacitor loaded conductor loops. As you can see here, these conductor loops are nothing but inductors, right. So, you will see the shielding performance of an array of such loops. Okay. So, the magnetic field source again in this case is a current loop with a radius of 8 centimeter, and you see the unit elements of the metamaterial are also current loops which are having radii of 0.8 centimeter, and the distance between the elements is maintained to be 7 centimeter. So, what is done here to improve the shielding? You can introduce inhomogeneity additionally in this metamaterial, and that basically improves the effectiveness of the shielding even more. So, what is happening? So, the inhomogeneity in this metamaterial can be engineered by tuning the resonance behavior or resonance frequencies of each individual elements. Okay. So, this tuning basically allows you a control over desired current values, right. So, how you can achieve this? The methods to achieve this will include, first you can change the capacitance values, okay. Then you can also think of changing the inductors, okay, and you can think of using inductors or two inductors in series that will modify and you can also think of modifying their mutual inductance between these two by changing the distance between the inductors. So, there are different ways you can change this resonance of individual elements, and you can create inhomogeneity, right. So, once you change you create some inhomogeneity, you can see. So, this is for a homogeneous metamaterial for the same size and everything. You see here the magnetic field strength is around say minus 80 to minus 100 dB, okay. But when you introduce this kind of inhomogeneity by altering the capacitance or the inductance or the mutual inductance effect for different layers, you can see that you are actually able to get almost minus 180 dB field, means it is almost negligible here. So, you are getting very good shielding in this particular case, and that is obtained by changing the capacitance values, right. So, what we learned from here is that inhomogeneous metamaterial can give better shielding as compared to the homogeneous metamaterial and the regular material of high or low permeability, right. Okay. So, now if you recall, you will remember that we have discussed this several times in our earlier lectures, that engineered materials and the materials we are interested in this particular course is basically the metamaterials, right. So, what are the key characteristics? The first thing you have to remember that the periodicity that we are discussing here is of the order of lambda by 10. That is, typically the size of the unit cell or the meta atom will be 1/10 of the wavelength that is interacting, okay. So, that is very important in achieving the desired resonance. The second thing is that the oscillating currents that is there in each meta atom, they basically emulate atomic resonances, okay, and this behavior of the electrons within the conductive elements of the metamaterials mimics the kind of resonance happens in atoms, and that leads to a very strong interaction with the electromagnetic field. So, finally, your light matter interaction improves, right. So, we have seen that the resonant metamaterials basically achieve their unique properties through their resonating unit cells, okay, and these structures are designed in a way that interacts strongly with the magnetic field, electromagnetic field at specific frequency. So, you basically try to match the resonance of the structures with the incident field's frequency, okay. And important parameter here to remember that we are talking in terms of a length scale which is lambda by 10, right. And this we have already discussed that the oscillating currents in this meta atoms basically emulate the atomic resonances, and because of which people have been able to demonstrate left hand metamaterials where both permittivity and permeability can be achieved negative over a particular frequency range. You can also have a refractive index less than 1 and so on. Now, there is another type of metamaterial which is called non-resonant metamaterial. So, here the meta atoms are not basically resonant type, right. So, non-resonant metamaterials rely on very different mechanism as compared to the resonant metamaterials to achieve their properties. So, you can see that they are not dependent on resonances, right. So, what are the key characteristics of this kind of non-resonant metamaterials? The first thing is that here also the period should be much smaller than lambda, and there are no current oscillations or wave scattering happening in this case. So, the overall structure is behaving like a metamaterial. So, here you have greater tolerance, okay, to any kind of structural deformity, okay, and because there are no current oscillations or wave scattering, they do not rely on oscillating currents or strong scattering properties for their functionality, right. So, what are the examples of this kind of metamaterials? They are anisotropic metamaterials, they are hyperbolic metamaterials, and these metamaterials exhibit different properties depending on the direction of propagation of the electromagnetic waves. So, another important metamaterial that we will encounter today is chiral metamaterials. Now, what is chiral, or you can say what is chirality? So, chirality basically refers to a geometric property of a structure that lacks any mirror symmetry plane, right. So, a chiral medium is basically composed of some particles that cannot be superimposed on their mirror image. So, you can take an example here. So, you take your right hand and bring it in front of a mirror, you get the reflection which looks like your left hand. Now, if you bring them together, you will see that they will not be superimposed, right. So, due to this kind of chiral asymmetry, any medium that has got unit cells, okay, or meta atoms made of this kind of chiral structure, they will basically exhibit different responses to a left circularly polarized right to a right circularly polarized right. So, these two different polarization will see different kind of responses, right. So, in the 1910s, okay, Lindemann extended the concept of optical activity from visible light to radio waves, okay. So, he used helical coils as artificial chiral molecules, and since then, the chiral media in the microwave region has been applied in various technologies such as antennas, polarizer, waveguides, etc. So, in 2003, Tretiakov and his group, they proposed the idea to fabricate a metamaterial that is composed of chiral particles such as helical wires to get negative refraction for one of the circular polarizations with kappa much larger than square root of epsilon mu. Now, what is this kappa? That is called the chiral parameter. So, it is a key parameter that basically describes the optical property of the chiral materials, particularly in the context of metamaterials and chiral media, right. So, it basically quantifies the degree of chirality, which basically refers to the handedness or non-superimposability of an object with its mirror image, right. So, in essence, you can say that a non-zero chiral parameter indicates that this material interacts differently with left circular and the right circular polarized light. So, in natural chiral materials such as quartz or sugar solution, you will see the chiral parameter kappa, which can also be calculated as the difference between the two refractive index by 2. So, that is n RCP, right circular polarization, minus n LCP, left circular polarized light. Okay, the refractive index that you see for these two different polarization divided by 2. So, that chiral parameter is much smaller than 1 in the case of natural chiral molecules, and you will see that square root of epsilon mu is very large than 1. That means, in such a material, negative refraction is not possible. Now, in chiral metamaterials, kappa, this chiral parameter can also be a complex number, where you will see that the real part basically relates to optical rotation, that is basically the rotatory power, and the imaginary part will cater to circular dichroism, that is basically the difference in the absorption between the two circular polarized lights, LCP and RCP, right. So, now in the case of chiral metamaterials, you also have a concept called chiral nihility, right. So, that happens when epsilon and mu are near 0. So, in that case, even small kappa chirality can also lead in negative refractive index for one circular polarization. Okay. So, in 2004, Surgeon Pendry basically proposed a microwave chiral metamaterial, which was using this kind of twisted Swiss rolls, okay, as metaatoms, and as long as the chiral parameter kappa was large enough, a negative refraction could be obtained in chiral metamaterials. So, this was shown in after 2004. Okay. So, what happens for chiral metamaterials with negative refractive index? You can see that the negative refractive index can be achieved by ensuring optical activity in chiral metamaterials or nanoplasmonic structures. Okay. So, this enhancement can be done by rapidly rotating the electric field direction of a linearly polarized wave over short distance in a chiral medium. So, I will show you some figures of that. So, in figure A, you can see this is a bilayer chiral structure, which is a twisted double rosettes kind of structure that can be used to achieve giant polarization rotation. Figure B basically shows a double layer array of twisted crosses, okay, and this is the structure. So, this can also give an negative refractive index from an effective bilayer design. This figure C actually shows a conjugated bilayer Gamadian array. So, this kind of a swastik symbol, okay, the conjugated one. Okay. So, that is like you have got two on the opposite sides of a dielectric slab, and then you have metamaterial made from that. Okay. So, what you see that this kind of structure breaks the mirror symmetry along the normal plane, that enhances the chirality, and a strong chiral metamaterial can have negative refractive index for one circular polarization around the resonant frequencies. So, figure D shows another kind of structure, which is basically a chiral resonator array made of gold, and that also demonstrates negative refractive index. Okay. Figure E shows conjugated double Z or Z kind of structure. Okay. So, that also enhances the optical activity through local field enhancement between the nano gaps present here, and these are all made of metal. So, you will see that they also have lot of optical activity, and to strengthen the intermolecular capacitive coupling, you can actually use a conventional conjugated Gamadian kind of structure that can be morphologically transformed into this kind of conjugated double Z metasurface kind of structure, right. So, the very small gaps that you see between the adjacent metallic elements basically increase the intermolecular coupling, right, and that can be characterized by electrical capacitance. Okay, here also you can see the same thing. So, here you are basically using this conjugated double Z metamaterial composed of copper wires. So, these are copper wires on Teflon substrate. So, we can also see 3D chiral metamaterials, which are especially working for optical frequencies. Okay. They consist of building blocks with feature size in nanoscale level, and they have much complex geometries. So, they are more intricate than chiral metamaterials. So, the fabrication processes typically involves top down methods, something like cuts and shapes of the materials using ion beam lithography or electron beam lithography or even direct laser writing. If you think of bottom up assembly, they will basically deal about assemblies of small components that add up to give you complex shapes. Okay. So, here you can see one such 3D chiral metamaterial, which is basically a 3D array of chiral split ring resonators, okay, that forms a isotropic chiral metamaterial, right. Here is another example that displays a 3D gold helices like this, that can be used as a broadband circular polarizer in the mid IR range. Okay. So, this particular device can also be used, or metamaterial can also be used for circular transmission conversion from LCP to RCP and vice versa. That depends on the length of this helix, their pitch and the radius of this helix. Okay. Also the wear radius. Okay. All these parameters play important role. And the fabrication process here basically involves direct laser writing of the helical pores, and that is followed by electrochemical deposition of gold, and you can finally get this kind of gold helix, 3D gold helix array, right. Next we move on to some sort of self assembled chiral metamaterials. So, when you compare with top down fabrication methods, this self assembly technology provides an alternative bottom up approach for realizing structures at the nanometer scale, which are cost effective and yet highly tunable, and they also work in fast manner. Okay. So, we will see that there are certain challenges in nanoscale structures when they self assemble, because you have to play between a balance of different kind of forces acting at the nanoscale, something like van der Waals force, capillary forces, then you have static or transient electromagnetic forces, you have different kind of convective and friction forces and so on. So, this basically allows precise control over the metallic nanoparticles with varying chemical compositions, geometries and sizes. So, they result in plasmonic metamaterials that has got tunable dimensions, programmable nanoscale precisions and so on, right. So, one such method to make self assembled chiral metamaterials is to use DNA base pair interactions that helps in assembling these plasmonic chiral nanoparticles. The plasmonic nanoparticles are typically the gold and the silver nanoparticles. Here we are talking about gold nanoparticles. So, how they work? The DNA is basically used as a scaffold to assemble the gold nanoparticles into this kind of a pyramidal geometry. So, you can see how it works. Okay. So, this pyramid structure is basically composed of two pairs of nanoparticles with different size, okay, as you can see, that allows tuning of intensity, the spectral response and handedness of the circular dichroism. So, once again circular dichroism is nothing but is a type of absorption spectroscopy that basically measures the difference in the absorption between left handed and the right handed circularly polarized light. So, this is typically a feature that is offered by this chiral molecule. So, here the chiral metamolecule, you can say, basically offers this kind of feature. So, by adjusting the separation along the symmetry breaking axis, you can also get this kind of chiral response. So, as I mentioned that this method is not only limited to gold, you can use any other metallic or semiconductor particles for this purpose. Okay. Now, you can also think of using bifacial DNA origami templates to assemble chiral nanostructures involving metallic nanoparticles that you can see here. The fabrication, in this case you are talking about 3D chiral metamaterials that uses 4 gold nanoparticles. So, the figure particularly shows a rectangular DNA origami template which has got 3 binding sites on the top surface, and then you have one binding site on the bottom which is aligned below the top binding site. So, in the, if you see, this is the achiral structure. So, there is no chirality in this, there are just 3 binding sites on the top surface, but when you put one nanoparticle at the on the bottom, so that gives you one kind of handedness. So, this will kind of give you left handedness structure. If you do on the other binding site, that will give you another kind of handedness. You will see that you are able to get a control over the chirality of this kind of 4 particle nanoparticle system, which are assembled using bifacial DNA template. So, you can get both left handed structure or right handed structure, and you can see their response, their circular dichroism, okay, and they show different chiral properties, right. So, you can also see another type of self assembled chiral metamaterial in this particular slide. So, you can understand that a characteristic bisignate circular dichroism spectrum can be observed in the case of left and right handed chiral nanostructures when you compare them with the achiral ones. Okay. So, here what is shown is basically a chiral chiral plasmonic film that is basically made by embedding gold nanorods. So, the yellow ones are basically the gold nanorods that you can see. They are embedded in a self assembled cellulose nanocrystals, okay, and they have some chiral arrangement. Okay. So, this plasmonic chiral structures can be realized by binding chiral molecules with these metallic nanoparticles. So, what you see here is that you can also use some sort of peptide molecules with your gold nanoparticles, and they can also give you some sort of chiral activity. So, this particular graph basically highlights that the chiral dichroism can be enhanced. So, there is a clear difference between the property of bare gold particles with gold particles bonded with peptide molecules, and you can see that they have chiral responses, right. So, what you understood that you can introduce chirality in different manner. You can either embed gold nanorods in a self assembled cellulose nanocrystals with some chiral arrangement like this, okay, or you can have peptide molecules bound to gold nanoparticles that can also induce chiral dichroism. So, these are different ways you can realize chiral metamaterials, and they will show different response to left hand circular polarized light and right hand circular polarized light. So, with that we will stop here. We will discuss different types of engineered metamaterials and their applications in the next lecture. If you have got any doubt regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.